Hello guys, I've seen a lot of people struggling to control heavy loads and also failing to secure their loads. So today we are going to look at different switching modes and also how you can secure your loads using microcontrollers. So a lot of people, they struggle when it comes to microcontrollers, especially the Arduinos and your peak microcontrollers. Let's say maybe, for example, you want to control a load which is 24 volts DC. So a lot of people, they struggle doing that. So today we are going to look at some switching configurations that you can use. So basically, so this is the first configuration that we have. This is the most common type of switching that we have. It has got an N-channel Mosfet here. So and our so this is our load motor. This is a 12 volt VDC motor. So we are going to control this motor using this configuration. So this one is called a low side switching configuration, and our motor is connected our motor is connected to the drain of the MOSFET and the power, and then it gets its ground through this MOSFET. So the main disadvantage of this configuration is that you don't have direct access to the ground. You only access the ground via this MOSFET. So if you have got any errors in your circuit, and you have got a short circuit in your circuit, you are likely to damage your circuit because you don't have a ground. So it is much safer if you to ground your load first before you get the power. So in that configuration where you connect your load to the ground via the source of the MOSFET, is called the high side switching. So let's go back to this configuration and take a look at it. So basically, here we said our ground is connected to the source and our motor is connected to the drain, and we have got the gate which is being activated by this signal, which is a 5 volt signal. So this MOSFET that we have here is a logic level MOSFET. So let me just start the simulation and take a look at the circuitry. Yes, so yeah, and we are running. So let me just close this circuit. So I close this switch. So we are getting a 5 volt signal here, and then it activates the MOSFET and powers up this motor. So basically, in the motor we have got our power here, which is 12 volt, and we are accessing the ground here. So this is the first configuration that we have. So this one is a low side switching N channel. So this is the most configuration that's being used by many people, but I dislike this configuration because your motor is directly connected to the source and to the power. So if you have got any voltage spikes or any kind of errors that you have in your circuit, you are likely to damage your load. So let me just stop this and let's go to the high side switching N channel. So now we can just change the configuration and go back to and connect our motor, which is our load, to the ground first, so that we protect our load. So now for this circuit, now we have got a problem here, because let me start again the simulation. Yeah, we are running. So let me just stop this. Yeah, so now if I start this, we have got our signal which is coming in here. So if I close here, we can actually see that there's nothing which is happening here, right? So so now this circuitry it's not proper, because now we have got a voltage difference of 0 between our gate and our source. So now we need to have a voltage difference between our gate and our source, so that we can have a current which is flowing in this direction. So we'll come back to this one. So as we all know that we have got different types of MOSFETs, which are N channel and P channel. So let's look at a high side switching P channel. So now in this configuration here, we've got a high side switching P channel, and we have connected our motor to the ground, and then we have got our gate here. So here I've got a switch here, a three-way switch. So in our drain, which is connected to the which is also connected to this power. So now if I so now we have got alright, let me stop and show you the power that we have here. So we have got a 12-volt power source here, and then this is ground. So let me start again. Right, so if I move on to the ground, we have got the circuitry. It actually works. So not works as I sorry. We have got a complete circuit here because we have activated the MOS. We have activated the MOSFET. So what is happening right now is this point here, it has got a zero potential. It has got a zero potential. We've grounded this point here, and you've got a 12-volt potential at this point. So now for this configuration here, at this source here, so if we have got a potential difference at our source here, we activate our MOSFET. So now if we go to this 12-volt here, our motor should stop. So it has stopped. The reason being, we have got a 12-volt we have got a 12-volt potential here and a 12-volt potential at that end there. So now the potential difference is 0, so we don't have any voltage across the gate of the MOSFET, so we don't have any current which is flowing through this. So now the reason why we don't use we would like not to use a p-channel MOSFET in this configuration is because of the resistance, the RDS of this MOSFET. So if our load is, if we've got a higher load here, and most MOSFETs here, they have got an RDS of about 0.8. So for this one, just take for an example, this is an RF 9510. So the RF 9530, they've got an RDS of about 0.8 ohm. So if you've got larger currents which are flowing through, which means that the MOSFET starts to dissipate, and we don't want that in our circuitry because we lose a lot of power. So we should use an N-channel MOSFET, because N-channel MOSFETs for this one, which is the IRFZ44ZL, it has got an RDS of 0.0053 ohm. So this is very good for our design. So now if you want to use an N-channel MOSFET in a high side switching circuit, we have to use what is known as a bootstrap circuit. So this is the bootstrap circuit. So I'll just take you through every component that we have here. Right, so we have got our, let me stop this. So we have got our load here, and is connected, the motor terminals are connected to the ground and the source, and we have got the power here, which is connected to the drain of the MOSFET, and we have got the gate here, which is being driven by an NPN transistor, and then this transistor base is being activated by a signal from our microcontroller, which is a logic level. So now for this setup now we've got also this diode, which is a Schottky diode, just to protect our circuit, because this is an inductive load. For example, if we've got the lights, if we've got any inductive load, you're supposed to put this diode. So what happens now, if this let's start from this side, because this transistor is the one which is controlling the whole circuit. So now if you've got if you don't activate this transistor here, it means that here is open at this side. So now if this side is open, which means that we are not grounding this point. So this point here, it means that it has got a voltage, the voltage difference of this voltage here, which is a 12-volt voltage difference. So now we've got 12 volts here. So if we've got 12 volts here, which means that we are activating this MOSFET here. So if we activate this MOSFET here, we'll get a 12 volt which is coming through this side, and also through a charge from this capacitor. So now let me go back again and start when we actually activate this, because this is the normal operation of this that we want. So now if we activate this, right, so let me start the simulation, then I'll show you what I'm talking about. So if we activate this point here, it means that we have grounded this point, because this now is a complete path this side. So now this point is at a zero, is at a ground level. So if it is at a ground level now, which means our MOSFET is not activated. So if it is not activated, so which means our current flows through this diode, through this capacitor, and through the ground. So it means that our capacitor now, it charges. This one is getting a positive, then this one is getting what, a negative, this plate, this side of the capacitors. So now our capacitor charges through this path right here. So now when we switch on now if we switch on now our circuitry, then we get a 12 volt potential at this side. And if we get a 12 volt potential at this side, which means that we actually activate this. So which means that the potential is what the gate to the source voltage is not 12 volt, and also the voltage across this motor is not 12 volt. So now we have got a potential difference now of 0. But now because of the capacitor now, we have this 12 volts here and another 12 volts here. So which means now we get two series voltage sources, which makes it 24 volts. So if we got a 24 volts here and a 12 supply here, which means that we have got a voltage difference between our gate and our source, and we activate our MOSFET. So that was the difference with this one, because in this one now we're having a potential difference of 0, because we're getting a 12 volt here and a 12 volt in the 12 volt here, which makes it a 0 potential difference between the gate and the source. So our MOSFET will be off. But for this one now, we are bootstrapping, which means that we get 24 volts from this power supply, from this power source here, and this capacitor, it charges up to that voltage here, and we get those two voltages to series up and make 24 volts, so that we can actually activate this MOSFET. So now this circuit now, it's mainly used for maybe hammering, if you know hammering circuits and switching circuits. We can use this type of configuration. So now for this configuration now, this is the way that you're supposed to use an N channel as a switching element. So now this is called a bootstrap high switching N channel configuration. So yeah, this is it. So in the next tutorial, I will just show you how we control this type of configuration from a microcontroller. So we'll remove this power source here, which is a 12 volt. Let me pause this, which is a 5 volt signal. So we're getting our 5 volt signal from our microcontroller, which is an Arduino or a PIC microcontroller.